All right, folks, so we're on 26.2, which is the nephron. We're going to talk about the functional unit of the kidney called the nephron. All right, so first of all, you looked at this anatomy here before, and you know what the pyramids are. This is a pyramid, and you know what the cortex and the medulla is. The pyramids make up the medulla. These columns, actually, though, are extensions of the cortex down in between pyramids. So that's actually cortical tissue, even though there could be an argument made that it's in the medullary area, but it's really cortical tissue dipping in between the pyramids of the medulla. The tubes, we'll talk about the nephron tubes here in a second. Part of them, they start in the cortex, they end up in the medulla, and they end up draining into these minor calyces here. Minor, like this is a minor calyx, that's a minor calyx, that's a minor calyx, that's a minor calyx, that's a minor calyx, another one. Two or more minor calyces drain into a major calyx. That's a major calyx. That's another major calyx right here because two minor calyces, another major calyx. All of these major calyces drain into what we call the renal pelvis, and then the urine goes down into the ureter. So this is the kidney in a nutshell. But let's look deeper into it and look at the nephron. This is just the blood flow. I do want to point out one thing because there's a video in the last section. The video in the last section called that artery and that vein interlobular, and it is called interlobular. I don't typically use that nomenclature. I call them cortical radiates, another name for them. And the only reason I don't really care, I don't mind using either word. It doesn't matter to me. But this artery and this vein are called interlobar. And I've always found that students confuse interlobar with interlobular. And therefore, what I do is I use the word interlobar, which I don't know if there's another, I don't think there's another word for it. And up for the interlobulars, I call them cortical radiates to alleviate some of the confusion. That's all I do there. Let me just tell you a couple other things so when you get to another course, it doesn't surprise you. Our book goes from, well, this is the renal artery, then you have segmental arteries here, and then you have these interlobar arteries here. All right. Now, some other books, when you have this segmental artery and it bifurcates here and here, some other books will actually call those lobar arteries. And then the lobar arteries bifurcate into the intralobar arteries, and then the arcuate and cortical radiates, etc. So some books use the word lobar artery. They have another naming mechanism, really. And even right here, if this is the renal artery and it bifurcates and that's segmental, then that would be lobar because you rename it after the bifurcation, and then that's interlobar. Now, coming back out, your book doesn't even use segmental veins. It goes directly from the interlobar veins to the renal vein. So it doesn't call this a segmental vein, and it definitely doesn't use the word lobar vein. Now, some books do. This would be, well, this one here would be interlobar vein, and segmental and renal. Okay, that's true there. However, this one here would be interlobar, lobar, and then where it joins this one, you have segmental and renal. So as I'm pointing out, what I'm just pointing out is the way your book does it is fine, but you'll read a Gray's Anatomy or another text or another book, and you'll see a slightly different naming system for these vessels. And that's fine. I just want you I want you to learn what your book has to say, but I want you to realize that some literature sources treat it slightly different. All right. Now, the nephron is the following. The nephron is this renal corpuscle right here, which is the Bowman's capsule plus the capillary bed called the glomerulus. The glomerulus equals the capillary bed. What happens is the afferent arteriole goes in and the efferent arteriole comes out, but that indeed is a capillary bed. So the glomerulus and the Bowman's capsule together are called the renal corpuscle. So the nephron is the renal corpuscle, this proximal convoluted tubule, this loop of Henle, this distal convoluted tubule, and that's it. The collecting duct right here is not part of the nephron because hundreds of nephrons drain into one collecting duct. So how can the collecting duct be part of one nephron? And the answer is it can't. So that's the nephron. And this is not even the picture that shows you the nephron the best. I'm just showing you the nephron and getting the words out there. I'll do it again. Notice there's two flavors of nephrons here. Let me erase all that. The two flavors of nephrons are these cortical nephrons, the ones high in the cortex, and these juxtamedullary nephrons, the ones lower in the cortex. The cortical nephrons are about 85% of all nephrons, and the juxtamedullary nephrons are about 15% of all your nephrons. However, I would contend that the juxtamedullary nephrons, even though they're numerically less of them, they are even more important in concentrating your urine. And that's because they have a long loop of Henle that dips deep into the renal pyramid. And we'll talk about why on that particular physiology right there. So cortical nephrons and juxtamedullary nephrons. This is the blood flow, and you can see that afferent arterioles go into the capillary bed and efferent arterioles come out of the capillary bed. Now, if you are a cortical nephron, the efferent arterioles go to peritubular capillaries. However, if you are a juxtamedullary nephron, the efferent arterioles go to vasa recta. Let me go back. So the efferent arterioles up here from this cortical nephron would become peritubular capillaries, whereas the efferent arterioles from this juxtamedullary nephron would become vasa recta capillaries. So this picture right here is obviously showing you blood flow in a cortical going up to a cortical nephron, because the capillaries that's being formed there is the peritubular capillaries.
The functional filtration unit of the kidney is a microscopic structure called the nephron. Each kidney contains approximately 1.3 million nephrons. Each nephron consists of a renal corpuscle and a renal tubule. The renal corpuscle is a bulbous structure in the renal cortex, consisting of a capillary network called the glomerulus and a surrounding glomerular capsule, also known as Bowman's capsule. Blood vessels enter and exit the renal corpuscle at its vascular pole. The tubular pole is continuous with the renal tubule. The glomerular capsule has two layers. The visceral layer envelops the capillaries of the glomerulus. It is composed of specialized epithelial cells called podocytes, which have multiple interdigitating foot-like processes called pedicels. The parietal layer is a simple squamous epithelium that forms a capsule around the glomerulus. The capsular space lies between these two layers. Water and some solutes of blood plasma pass through a filtration membrane formed by three components of the glomerulus. Small pores in the capillary endothelium called fenestrations, a basement membrane between the endothelium and the podocytes, and narrow spaces called filtration slits between pedicels. The renal tubule is composed of a proximal convoluted tubule, a nephron loop, and a distal convoluted tubule. The extensively coiled proximal convoluted tubule originates at the tubular pole of the renal corpuscle and is continuous with the nephron loop. Each U-shaped nephron loop, also known as the loop of Henle, consists of a descending limb that extends into the medulla and an ascending limb that returns to the cortex. The nephron loop is divided into thick and thin segments. The thick segments are lined with simple cuboidal epithelium, and the thin segments are lined with simple squamous epithelium. Beyond the ascending limb of the nephron loop, the renal tubule coils again to form the distal convoluted tubule. Several distal convoluted tubules drain into collecting ducts that pass through the medulla of the kidney. These merge to form papillary ducts that drain into a minor calyx. As fluid passes through the renal tubule, useful solutes move out of the tubular fluid and return to the blood, and waste products in the blood move into the tubular fluid, ultimately to be excreted in the urine. Two types of nephrons can be identified based on their location within the renal cortex. Cortical nephrons, which account for 85% of the nephrons, have their glomerulus near the periphery of the cortex, and nephron loops in the outer medulla. The remaining nephrons are called juxtamedullary nephrons, because their glomeruli are located at the corticomedullary junction, and have relatively long nephron loops that extend deep into the medulla. Blood from interlobular arteries enters the vascular pole of each glomerulus through an afferent arteriole. A juxtaglomerular apparatus is located at the point where the afferent arteriole enters the renal corpuscle. The juxtaglomerular apparatus has three parts: the macula densa, composed of specialized cells of the distal convoluted tubule; modified smooth muscle cells known as juxtaglomerular cells; and extraglomerular mesangial cells. The juxtaglomerular apparatus monitors blood sodium concentration and adjusts glomerular filtrate volume through hormonal feedback mechanisms. The efferent arteriole from each glomerulus enters a second capillary network. For cortical nephrons, a peritubular capillary network surrounds the proximal and distal convoluted tubules. This capillary network drains into interlobular veins. In contrast, efferent arterioles associated with juxtamedullary nephrons enter capillaries known as the vasa recta that surround the descending and ascending limbs of the nephron loop. From the vasa recta, blood also flows into interlobular veins.
All right, that video was just chock full of information. You should probably watch that twice. And let me see if there's anything I particularly want to talk about. I will tell you this. I'll remind you from Bio 203 that you learned about fenestrated capillaries. So I think they show you the fenestra here. Yep, right there. They show you the fenestra of the fenestrated capillaries. These fenestra are probably about 90 nanometers diameter. So you can see the fenestra, or these holes right here, and again they're about that's about 90 nanometers. And then these podocytes have slits, and you can see the slits here, and they're about 9 nanometers. The slits are narrower than the fenestra. So nothing will filter being greater than 90 nanometers. Well, first of all, nothing gets through the fenestra if they're greater than 90 nanometers. And then if they're less than 90 nanometers, they won't get through the filtration slits here of the podocytes, between the podocytes, if they're greater than 9 nanometers. And in addition, there's a basement membrane, and that's negatively charged, so charge has something to do. And I'll talk about filtration a little more in the next section. This section is only the nephron. But you can see the podocytes sitting on the glomerulus, and they add to this filtration membrane. A lot of information here. Okay, this I want to talk about a little bit, and let me get to the end of it. Let me start right here. If you take something that has been filtered, that's in the tubular fluid, and you take it, so it's been filtered, and you put it back into the bloodstream, that's called reabsorption. However, if something hasn't been filtered, it's still in the blood, but you put it into the filtrate, that's called secretion. So in other words, what I'm saying to you is, you may filter something your body wants, like glucose. No problem, we can reabsorb it. Additionally, you may fail to filter some waste product that you want in the urine. No problem, we can secrete it. So you can see that the filtrate is not static. You can add to it and subtract from it by reabsorption and secretion. So that's a big concept there. This juxtaglomerular apparatus, these juxtaglomerular cells are smooth muscle cells. They can detect blood pressure in here in the afferent arteriole. These mesangial cells have gap junctions, and what we think is that they are the way that these smooth muscle cells actually talk to the macula densa cells. We think that signals from the juxtaglomerular cells travel through the mesangial cells and then can communicate with the macula densa cells. The macula densa cells monitor sodium concentration in the filtrate. Now, all three of these things together are called the juxtaglomerular apparatus. And the JGA, the juxtaglomerular apparatus, is going to be involved in the renin-angiotensin-aldosterone system. So the JGA is going to be the beginning of what we call the renin-angiotensin-aldosterone system. And we abbreviate it RAS system. We abbreviate that RAS. You learned that in Bio 203 in I forget which chapter, the blood chapter. Oh, maybe not. Yeah, I think the blood chapter, cardiac chapter possibly. You learned it probably in the No, you wouldn't have learned it in the respiratory chapter. Other than the lungs do have an enzyme called ACE, angiotensin converting enzyme. But anyway, you learned this renin-angiotensin-aldosterone system before. You learned it in 203 and 204. And I think we talked about it in the endocrine chapter earlier this year. So you have heard it before, you're going to hear it again. And then when you get to, if you're pre-nursing, when you get to your nursing program, you're going to hear it again. And I know you do because students come back to me and they say, hey, thanks for hitting that so hard, because the nurses go crazy on it too. So there you go. All right, so that's it for that. So this is the JGA. We just actually talked about it. The JGA is composed of the macula densa cells. They monitor sodium concentration in the filtrate. The bottom line is this: if you have a lot of sodium in the filtrate, it means that the filtrate's moving very quickly, because our body's really good at conserving sodium. We reabsorb most of it. If the filtrate's moving very quickly, it's because you are filtering a lot, and that could be due to a high blood pressure or something like that. So it monitors the sodium concentration and adjusts accordingly. The smooth muscle cells, these juxtaglomerular cells in the afferent arteriole, they monitor blood pressure, and if the blood pressure drops too low, they'll secrete renin. These mesangial cells right here, these are what we think they are, is they're filled with gap junctions, so we think they're a communication liaison between the JG cells and the macula densa cells. All right, so that's the juxtaglomerular apparatus. And again, the nephron is the renal corpuscle, the proximal convoluted tubule, the loop of Henle, and the distal convoluted tubule. Now, this loop of Henle can be divided into the descending limb of the loop of Henle and the ascending limb of the loop of Henle. Now, this picture tells you volumes. All right, this is volumes. If you look right here, everything, just look at the key right here. First of all, green is filtrate. So this is filtrate. Filtration occurred in Bowman's capsule. If it's a solid line, like here and here, they are solid lines, then they are obligate. Solid line is obligate. Equals obligatory. That means it's going to happen no matter what. There is no hormone that adjusts it. It's an obligatory reabsorption or obligatory secretion. If it's coming out, it's reabsorption. If it's going in, like there, it's secretion. All right. If it's tan, it's a solute. If it's blue, it's water. So this is let me erase some of this. This is reabsorbing a solute. This is reabsorbing water. This is reabsorbing a solute. This is reabsorbing water. This is reabsorbing a solute, and this is reabsorbing water. But if it's a dotted line, it's facultative. That means variable. Facultative, variable. And that is under hormonal control. I mean, in fact, it is variable. It's variable because it's under hormonal control. If the hormone is there, it does reabsorb or secrete. If the hormone's not there, it does not. You can see what our tubules are made of. Our proximal convoluted tubule, quite often abbreviated PCT, is made of simple cuboidal epithelial cells which have microvilli. That increases the surface area, of course, so you can see that. By the way, I went directly to the proximal convoluted tubule. Let's not skip the glomerulus. Capillaries are made of endothelial cells, which are simple squamous epithelial cells. So you can see that this is simple squamous epithelial cells. In fact, you can even talk about the cells that make up Bowman's capsule. And Bowman's capsule, the parietal layer is made of simple squamous epithelium, but the visceral layer is the podocytes. They're modified squamous cells. They're called podocytes. We have the loop of Henle. We have the thin segment and the thick segment. The thin segment is made of squamous cells, and the thick segment is made of cuboidal cells. So squamous cells here, cuboidal cells here, thin and thick. The thing with the loop of Henle is the descending limb is permeable to water, and the ascending limb is impermeable to water. There is no water reabsorption in the ascending limb. Matter of fact, you only see the tan arrow in the ascending limb. That's because the ascending limb is impermeable to water, but it is permeable to solutes like sodium. And then you can see the distal convoluted tubule. It's simple cuboidal epithelium as well. You can see the simple cuboidal epithelial cells right there. We will talk about principal cells and intercalated cells in the near future. We have principal cells and intercalated cells. You see these in the distal convoluted tubule and the collecting ducts. And really probably the end of the distal convoluted tubule as you get closer to the collecting ducts. You see principal cells and intercalated cells. All right, so that's a nephron. Oh, good. I didn't even have to write that. Towards the end of the distal convoluted tubule and into the collecting duct, we have these intercalated cells and these principal cells. They do have some slightly different, they're not major different physiological jobs, but they're slightly different. And some of them are responsible for hydrogen reabsorption or secretion, and other ones are responsible for electrolyte, sodium and potassium reabsorption and secretion. You can see that the same thing, dotted line, is facultative or variable. You can see that it can reabsorb or secrete water or solutes. So we'll talk about the collecting ducts when we get there. All right. Now, the collecting duct is not part of the nephron. Hundreds of nephrons dump into one collecting duct. But we still have to talk about the collecting duct. I mean, it's not, even though it's not part of the nephron explicitly, we still have to talk about it certainly because the nephron dumps into it. And this is the collage. This is the collage showing you the entire purple nephron dumping into the tan or yellow collecting duct. Remember, the collecting duct's not part of the nephron. Okay, this shows you a cortical nephron versus a juxtamedullary nephron. We already mentioned before that the efferent arterioles of the cortical nephron become paratubular capillaries, whereas the efferent arterioles of the juxtamedullary nephrons become vasorecta capillaries. By the way, we're talking about the juxtaglomerular apparatus and the juxtamedullary nephron. Juxta just means next to. So when you say juxtaglomerular apparatus, next to the glomerulus, JGA, juxta, next to the glomerulus. Juxtamedullary nephron, juxta, next to the medulla. And remember, this is the medulla, so the juxtamedullary nephrons are next to the medulla, whereas the cortical nephrons are high in the cortex. This shows you the efferent arterioles of juxtamedullary nephrons become vasa recta. Oh, that's showing peritubular. Here's the vasa recta. The efferent arterioles of juxtamedullary nephrons become vasa recta. The efferent arterioles of cortical nephrons become peritubular capillaries. Peritubular capillaries. That's the big difference. This Lupa Henle here does not dip deep into the medulla from a cortical nephron. See how this Lupa Henle hardly dips into the medulla at all, just a little bit. Whereas the Lupa Henle of the juxtamedullary nephron dips deep into the medulla. That means something because there's a salt gradient in here. There is a salt gradient in the medulla that we will come back to and talk about. All right, this is showing you this is just a table of the histology of these things. The renal corpuscle, you can read this, you can see this. We already talked about these being simple cuboidal with microvilli. We already talked about the thin segment of the Lupa Henle being simple squamous and the thick segment being simple cuboidal. We already talked about that. We already talked about the distal convoluted tubule. It's simple cuboidal. It doesn't have the same volume or number of microvilli that the proximal convoluted tubule does. It does have a few microvilli. Matter of fact, it says it right here. Few, if any, microvilli. There's a few in the distal convoluted tubule, but not much. In the collecting duct system, you can see that we have intercalated cells and principal cells, two different cell populations making up the collecting duct. All right, those are the cells of the nephron. Now, filtration and the filtration membrane. Filtration occurs out of the glomerulus into Bowman's capsule. So filtration occurs like that. We filter the renal corpuscle doesn't know what is good and what is bad in your body. So it just filters. So basically anything that can fit through the fenestra and then fit through the filtration slips between the podocytes, that is filtered. But the fenestrations are only 90 nanometers. And the filtration slits are only about 9 nanometers. So you really have to be smaller than 9 nanometers to be filtered. Our smallest protein, albumin, is about 9 to 10 nanometers. So even our smallest protein is really a little bit too big to be filtered. And there's another reason why proteins aren't typically filtered as well. So we'll talk about this filtration membrane. I got a better picture for you. All right, this is showing you, this is a weird slice of it actually. But here's your glomerulus, here's the fenestrations, the holes in the fenestrated capillaries. And then you have these filtration slits right here, right here. It's really a funny looking slice. I got to be honest, it's a funny looking slice of the glomerulus. I have a better slice for you. In addition, if you look right here, I have this basement membrane right there, right here. And that's negatively charged. So the basement membrane has a negative charge. And that means that not only does it have to be smaller than 90 nanometers to get through the fenestra, and then smaller than 9 nanometers to get through the filtration slits. But this basement membrane, by the way, it's called the dense layer. The dense layer is the basement membrane, and it's negatively charged. Not only does it have to be small enough to get through the fenestra and the filtration slits, but it also has to be neutral or maybe slightly positively charged, because two negatives will repel each other. So the basement membrane is negatively charged and will repel negative charges. Well, if you ask what's negatively charged in our blood, proteins are. The proteins in our blood are negatively charged. So proteins would have a hard time entering Bowman's capsule. This is a better picture because it's showing you a side slice. So here's the blood. Here's blood right here. Here's the fenestra. This yellow piece right here is the dense layer, basement membrane. And then these are the filtration slits right here. And so the filtration slits are about 9 nanometers. The fenestras are about 90 nanometers. And your basement membrane or dense layer is negatively charged. So that's looking at the filtration membrane from that slice. It's a little, this slice is just confusing to me. I get it. I mean, don't get me wrong. I can see what they're trying to show you, but because they sliced it in a funny way, it's harder to envision. This is easy to envision. And that's it. We'll come back to what drives filtration afterwards.